In this tutorial we're looking at section 9.4, which is on solving type 2 differential equations, okay, which are in the form dy dx equals f of y. Okay, so the idea with these ones is that we invert, integrate and transpose. So in this section we solve first order differential equations in the form of our dy dx equals f of y. So what we do is we find that dx dy is equal to 1 over dy dx. And we can say dx dy is equal to 1 over f of y, okay, because our dy dx is equal to f of y. Okay. Then we integrate with respect to y to find that we get x equals the integral of 1 on f of y dy plus c. And we finish off by rearranging for y. So we've got some worked examples we'll have a look at. So the first one is worked example 8, which is find the general solution to dy dx minus 4 times the square root of y equals 0. Okay, so what we need to do is rewrite this so we get dy dx equals our 4 root y. Okay, well that means our dx dy equals our 1 over 4 root y. Okay, then we can integrate, which means we'll get x equals integral of 1 over 4 root y dy. Okay, we bring our 1 on 4 out the front, means we've got 1 on 4, so the integral of, well, we can say 1 over root y, or you can say y to the negative a half dy. Okay, so that means that we can say then that x is equal to a quarter times by, okay, well, we need to add 1 to our power, which makes it y to the power positive a half. Then we've got to divide it by a half, okay, plus c. So that means we've got x equals 1 on 4 times 2 root y plus c. Okay, so that means we get x equals a half root y plus c. Okay. What we want to do is we want to rearrange to make y the subject. Okay, so what we can do is we can rearrange a little bit and say that we've got, well, a half root y equals x minus c, okay, which means we can times by 2 and say we've got root y equals 2x take 2c. Okay, and then what means, okay, what we do, since c is a constant, 2c is also a constant, so what they do, okay, is replace 2c with a, so we'd say root y equals 2x minus a, so y equals 2x minus a squared, okay, where a is just a constant. Okay, so there's nothing too technical with that worked example. Okay, we'll have a look over the page at worked example 9. We've got solve dy dx equals 4 minus 3y squared equals 0. So dy dx plus 4 minus 3y squared equals 0, given that y of 2 equals 1. Okay, so this one's a little bit more challenging. Okay, we've got a few more steps in this one. So we can say, well, our dy dx, well, that's going to equal our minus 4 minus 3y squared. Okay, which means what we want to do is again flip it, dx dy, okay, meaning that we've got negative 1 over 4 minus 3y squared. Okay, we can think of that a negative up here and we can integrate, so we say, well, x equals the integral of negative 1 over our 4 minus 3y squared dy. Okay. And we can think of this again just a little bit differently. We bring our negative out the front, okay, and we want to write this as 4 minus 3y to the negative 2 dy. Okay, so what they do is they go through and do our substitution. Okay, so I'll follow the way they've done it, but of course we do have our rule for using this. Okay, so what we'll do is we'll say, then, well, let u equal 4 minus 3y. Okay, our du dy equals minus 3. So our dy du equals minus 1 on 3. So dy equals negative a third du. Okay, that means then our integral becomes x equals minus the integral of u to the negative 2. Okay, because we don't have 4 minus 3y, we've got u now. Okay, times by negative a third du. So and say then that that's equal to 1 on 3 outside our integral of u to the negative 2 du. Okay, so that means then that x is equal to a third times, so negative a third times u to the negative 1 plus c. Or we can think of that as x equals negative 1 over 3u plus c. Okay, we can think of it like that. Okay, we can substitute back in now for our u. So we can say then now x equals minus 1 over 3 times our 4 minus 3y plus c. Okay, and now we know we've got some initial conditions here. So you know when x is 2, y is equal to 1. Okay, so what we can do is have a look at putting those values in. Okay, so when we do that, we get our 2 equals negative 1 over 3 times 4, and y was 1. Okay, so we'll take 3 times 1 plus c. So we get 2 equals negative 1 over 3 outside of 4, take 3 is 1 plus c. So 2 equals negative 1 over 3 plus c. Okay, so c is equal to 7 over 3. When we add on our third, we write as 7 over 3. Okay, so what we can say then is, we've got x equals our negative 1 over 3 outside of 4 minus 3y plus 7 over 3. Well, we've got to rearrange this for y. Okay, so we can then start working on that, and we can say we've got negative 1 over, actually not negative 1, say 1 over our 3 outside of 4 minus 3y plus, will equal 7 on 3 minus x. Okay, by bringing this over this side and our x over that side. Okay, so that means that we can say we've got 1 over 3 outside of 4 minus 3y is equal to 7 minus 3x over 3. Okay, so we can say then that 4 minus 3y equals 1 over 7 minus 3x. Okay, we can keep rearranging and get 3y equals 4 minus 1 over 7 minus 3x. Okay, so we're getting there. We can say our 3y then is equal to 4 outside of 7 minus 3x minus 1 over 7 minus 3x. Okay, just bringing our fractions together. Okay, so we can expand that a bit and say that we've got 28 minus 12x minus 1 over our 7 minus 3x. So 3y equals 27 minus 12x over 7 minus 3x. Okay, we can bring out our, that's it, 12. Okay, so we go 3y equals 3 outside of 9 minus 4x over 7 minus 3x. Okay, so we can do that. So when we divide by 3, our 3's are going to cancel out. And we get y equals 9 minus 4x over 7 minus 3x. Okay, and so x cannot equal 7 on 3. Okay, so a lot of it was just rearranging towards the end there. Okay, we'd found our c value, so we did have the equation here, okay, and then there was quite a fair bit of work to rearrange for y in this case. We've got one more example to do, okay, and then we're finished. Okay, So this is worked example 11. So this time we're saying that 2 times dy dx equals the square root of 16 minus y squared equals 0, given that y is 0 equals 0, okay, and we've got to state the maximum valid domain. So what we could do is rewrite the equation here. Okay, so we can say, well, we get 2 times our dy dx. It's going to equal negative square root of 16 minus y squared. Okay, and so we can say our dy dx is equal to our negative square root of 16 minus y squared over 2. Okay, we're going to flip it this time, so we can say our dx on our dy is equal to our negative 2 over the square root of 16 minus y squared. So, okay, and of course then we can integrate this. Try jumping ahead then. So we can integrate minus 2 over square root of 16 minus y squared dy. Okay, and so we know then that x equals 2 times the inverse cos of y on 4 plus c. Okay, from our identities, okay, that we have. What we're going to do is we're going to substitute x and y equals to 0. Okay, so we get 0 equals 2 inverse cos of 0 plus c. Okay, so when we go through that, we get c equals negative pi. So therefore we know that x equals 2 times the inverse cos of y on 4 minus pi. Okay, and now we've got to look at rearranging our equation. Okay, so we can say, well, 2 times the inverse cos of y on 4 equals x plus pi. Okay, and we can divide that by 2 and say that we've got our inverse cos of y on 4 is equal to x plus pi on 2. I have to come up here now. Okay, so that means we can say our y on 4 is equal to cos of x plus pi on 2. So y equals 4 cos of x plus pi on 2. Okay, so we're been rearranging that right through. Okay, what we can do though is make this look a little bit nicer. Okay, because what we can say then is that y equals 4 cos of x on 2 plus pi on 2. Okay, so we're doing this just so we don't have the fraction that we had in here. Okay, if you'd stopped here, okay, would you have gotten a tick on an exam? Most likely yes. Okay, this is just showing you how we can rearrange it to get rid of this fraction in case you have a question that's more of a show question. Okay, so when we do that, we can use one of our identities, one of our compound angle formulas, to say y equals 4 times cos of x on 2 cos of pi on 2 minus sine of x on 2 sine of pi on 2. We can then say, well, 4 times cos of x on 2. Okay, well, cos of pi on 2 is 0. Okay, minus sine of x on 2 times, well, sine of pi on 2 is 1. Okay, so that means that we lose this part altogether. Okay, and we're just left with, in here, negative sine of x on 2. So we can say we've got negative 4 sine of x on 2. Okay, so that's the form that they take us down to. Okay, so we might have to go through this process if it was, say, solve this, giving your answer in the form of, say, a sine of x on b, something like that. Okay, then we'd have to rearrange to this sort of form, otherwise we wouldn't really need to worry too much. Okay, so what we need to do is determine the domain for which the solution is valid. Okay, Well, we know here that we've got our inverse cos of our y on 4 from earlier equaled our x plus pi on 2. Okay, the range of our y part, the range of y equals inverse cos of x is from 0 to pi. Okay, but the modulus of y is less than 4. Okay, so we end up saying that we're going to be 0 is less than x plus pi on 2 less than pi. So you can rearrange that and we find that we get negative pi is less than x is less than pi. Okay, so that would be our largest domain, okay, that we could have, is from negative pi to pi once we rearrange this identity. So that's actually everything we have for this section. Okay, so they're pretty similar to the previous type questions that we've done in section 9.3. Okay, they're just slightly different in terms of doing our inverting step. Okay, so hopefully you can get through these questions without too many dramas.